Alright, this is going to be the video lecture for 4.2. We should be able to do this all in one video. So 4.2 is all about graphs of exponential functions. Like with linear functions, the graph of an exponential function is determined by the values for the parameters in the function's formula. To get a sense of the behavior for exponentials, let's start by looking more closely at the function f of x equals 2 to the x power. If we create a table of values for this function, we plug in -3, we get 1/8 out of that because that's 2 to the -3, which is 1 over 2 to the third power, which is 1 over 8. Similarly, if I plug in -2, 2 to the -2 power is 1/4, and so on. Notice here that this function is going to be positive for all values of x. Even whenever I plug in these negative numbers, I'm never going to get a negative number out. As my x values are increasing here, this function is also growing faster and faster, right? As I get farther to the right here in my x values, so between 0 and 1, this increased by 1, right? Whenever I increase the x value to 2, my output is now 4. When I increase the x value to 3, my output is now 8, right? Because this is doubling each time, the function is growing faster and faster as my x value increases. And as my x value decreases, this function is growing smaller and smaller. This is an example of exponential growth. If I look at a similar function, well, somewhat similar in a way, this is g of x equals 1/2 to the x power. Notice here that this table looks basically just my g of x values look flipped from the f of x values, right? Notice here that all of these y values are also positive. This function is still going to be positive for all values of x. But in this case, the function is going to increase, the function is going to grow as x decreases here, right? As I go farther to the left on this function, it's going to be going upwards. And this function is going to decay as I move to the right. You might notice, so since this is just it's basically the previous table, but flipped, that this function is going to be a horizontal reflection of f of x equals 2 to the x. And this is the case. And this should make sense because if I find f of negative x, this would have been 2 to the negative x, which is the same thing as 2 to the -1 raised to the x power. And this is the same thing as 1/2 to the x power. So we see that these two functions, f of x and g of x, are reflections of one another. And we have a few features of these graphs that we can look at. By a few, I mean we actually have quite a few. Graphically, if we have a function in the form f of x equals a times b to the x, a is the vertical intercept of the graph, b determines the rate at which the graph grows. When a is positive, the function will increase if b is greater than 1. The function will decrease if b is between 0 and 1. The graph of a times b to the x will have a horizontal asymptote at y equals 0. It will be concave up if a is positive and concave down if a is negative. Notice that if a is 0, this function just doesn't exist, right? This is just f of, well, I mean, it does exist, but it's a horizontal line instead of an exponential function. The domain of this function will be all real numbers. There's nothing that I can't plug into this function. The range of this function is going to be from 0 to infinity. And this value b will determine the function's long-run behavior. If b is greater than 1, then f of x will approach infinity as x approaches, where was I? Oh yeah, rather. Sorry, I I started reading midline from what I have right here instead of. Okay. If b is greater than 1, then as x approaches infinity, f of x also approaches infinity. And as x approaches negative infinity, f of x approaches 0. If b is between 0 and 1, then as x approaches infinity, f of x approaches 0. And as x approaches negative infinity, f of x approaches infinity. This is similar to what we looked at previously. Let's look at an example. This is an example where it's asking for us to sketch the graph, but we're not going to necessarily sketch the graph. Let's just look at some features of the graph, right? If I wanted you to sketch this, you'd probably just go to desmos.com. It would be no big deal to graph this, right? Instead, let's find the vertical intercept. Well, this is going to be at y equals a, right? So the vertical intercept here is going to be at y equals 4. That's the point 0, 4. Notice that this graph will also pass through the point, this graph also passes through the point, if I plug in 1, I get the point 1 4/3 on this graph. So if I wanted a second point to use to sketch this graph, for instance, then I can just plug in 1, and I'll always get whatever a times b is. In this case, a times b is 4/3 as my y value. So I always get the point 1, AB. Notice that because b is less than 1, right? B is 1/3. This means that the graph is going to be decreasing towards 0. And since a is greater than 0, the graph will be concave up, right? A is 4, which is greater than 0. And this also tells me about the long run behavior of this graph. I can see that as x approaches positive infinity, f of x is going to approach 0. We're going to have a horizontal asymptote at 0. And this is because b is less than 1, correct? And as x approaches negative infinity, f of x is going to approach positive infinity. And just for good measure, I have the graph of this function right here to confirm all of these properties that we have just discussed. Now let's look at a few examples of graphs to determine the effect that these values a and b have on the graphs of these functions. So first, let's look at the effect that this b has on the function. So we have 9/10 to the x power, 1/2 to the x power, 1/3 to the x power, 3 to the x power, 2 to the x power, and 3/2 to the x power. Notice here that the closer our value of b gets to 0, the less steep this graph is. For instance, this 9/10 to the x power graph is not very steep at all, right? In fact, it almost looks like a straight line. If we were to zoom out a bit, we might, or zoom in a bit, maybe, rather. This would probably look very close to a straight line. So the farther this value is from 1, the steeper the graph is going to become. Now let's look at the effect of a on these graphs. Notice here that as my value of a increases here, this is changing my vertical intercept. However, notice that the space between these graphs is also getting relatively substantial in some cases, right? This is because a is not a vertical shift. A here is a vertical stretch. this number A is a vertical stretch factor, not a vertical shift. It's essentially causing these graphs to bend upwards more quickly, which is causing these vertical intercepts to change, right? So this does have an effect on the vertical intercept because it's causing the graph to bend upward at a different rate. And here, let's match each equation with its graph. The easiest one to be here might be k of x, because k of x, notice that this is exponential decay, right? So k of x matches the red graph. This matches the... I can't believe I spelled red that way, but anyway. So k of x matches the red graph, right? It's the only one going in the opposite direction of the others. Then, from here, we might notice that h of x also has the same vertical intercept as k of x, right? They should both have a vertical intercept at 4. H of x is the one that's going the other way, though, because h of x is exponential growth. This means that h of x is the, I'm going to call that orange. I'm going to call that the orange graph. Now we're between g of x and f of x. They both have a vertical intercept at 2. G of x should be growing faster. So g of x is going to be the green graph. And this makes f of x the blue graph. Because g of x is a larger value of b, meaning that it's going to grow faster. Next up, let's look at transformations of exponential functions. Let's say we want to shift the function f of x equals 3 times 2 to the x, 4 units to the left. Okay, in this case, I'm trying to look at f of x plus 4. This gives me 3 times 2 to the x plus 4 power. And using my exponent rules, I can rewrite this as 3 times 2 to the x times 2 to the 4th power. 2 to the 4th power is 16, and 16 times 3 is 48. So this is the same thing as 48 times 2 to the x. So notice that a horizontal shift in an exponential function, so horizontal shift in exponential functions, this corresponds with the change in the initial value of the function. Now, looking at vertical shifts, let's say we want to take the same function, f of x equals 3 times 2 to the x, and I want to shift this down 4 units. Well, that would just be f of x minus 4. This would be 3 times 2 to the x minus 4. And there's no way to represent this as like some change in the initial value or anything. This actually shifts the graph down. And this causes me to now have a horizontal asymptote at, instead of y equals 0, at y equals -4. So this brings us to transformations of exponential functions. Any transformed exponential function can be written in the form f of x equals a times b to the x plus c, where y equals c is the horizontal asymptote. And due to this shift, the vertical intercept is now going to be at the point 0, comma, a plus c. So let's look at an example of using this. Let's find an equation for this exponential function. So notice here that it seems like we have a horizontal asymptote at y equals 5. As this is going to the left, this is leveling out at a y value of 5. This suggests that we have an equation in the form f of x equals a times b to the x plus 5. Now if I want to find a and b, I have to find two other points on this graph. Thankfully it looks like I have the point 0, 2, and what else? -1, 3. If I substitute in these points, I get, let's see, 2 equals a times b to the 0th plus 5. B to the 0th is just 1, so 2 equals a plus 5. Subtracting 5 from both sides, I get that a is equal to -3. Then f of x equals -3 times b to the x plus 5. If I substitute in this other point, 3 equals -3 times b to the -1 plus 5. Subtracting 5 from both sides, I get that -2 equals -3 times b to the -1. This is -2 equals -3 divided by b. If I multiply both sides by b, I get -2b equals -3. And dividing both sides by -2, I get that b is -3 over -2, which is +3 over +2. So my final formula here is f of x equals -3 times 3/2, or 1.5, I suppose you could write this, to the x power plus 5. And that's my answer. And that's all of 4.2, really.